very happy to be here in this brand new project, which falls a bit outside from our main research lines of our group, but well intersects with this last benchmarking efforts we have done during the last years. I will introduce a bit the group. So we are in an institute which is one of the comes from the founder of modern neuroscience, which is Santiago Ramón y Cajal. We are in Madrid, and our institute is basically 95% neurobiologists, and we are called the robotics guys because we are the only engineers in that institute. As you can see, the institute has 3 departments, and one of these is called the Department of Translational Neuroscience, which main goals is to transfer the methods and the evidence from neuroscience and try to translate it into patients and into new kind of therapeutic interventions. And in our group, we are part of this department. We are the neuro rehabilitation group, whose main goal is to develop machines to do better therapy, to better understand and better intervene on subjects. We are 4 PIs, you can see on the right, and this picture is always going to change over time because there are a lot of students that are turning. And I tried to simplify the research line. Because we are going in many directions, but I can say that we are focused on these 4 aspects. The first is the interaction between human and robots. We are developing basically exoskeleton, also other kind of machines like electrical stimulator for muscles and affer pathways. But basically what we would like to improve the interaction between the human and the robot to make the machine more transparent, more intuitive. And on the right you can see the bunch of projects. These are all European projects that have been in the last, let's say, 5 years. Some of them are running so far. Then there is the second part is benchmarking, which is actually the line which I'm personally going leading in this group, which is the benchmarking of exoskeleton, wearable robots in general, and also humanoid locomotion. Actually, this benchmarking effort started from a H2R project, which is this one, which was like a human-like bipedal robot. And now with Eurobench, I will talk in the next slides. A third line is the analysis of muscle coordination, restoration of muscle coordination. This actually very well linked with all the aspect of that has been talked by Imperial College colleague about passive dynamics or the role of muscles and all these stiffness modulation in human joints. And also, of course, we would like to restore this muscle coordination in impaired individuals. And the first line is we are developing neural interfaces, so implanted interfaces to better manage tremor in people with essential tremor, Parkinson's disease, but also to better, so we close the loop because we like to better also realize better interaction with robots. So using implanted interfaces to have this more efficient and more effective communication with an external machine. On the left side, you can see we are also coordinating the project InBots that has been also mentioned by Manolo, which actually cover all the aspects related to robotics, collaborative robots. So not only technical aspect, but also not technical aspect. We are organizing a conference actually this month. So if you don't know the conference is free, so you can participate. It's a virtual, of course. And also NI will be also presented there. So in this talk, I would like to focus mostly on the second line because it's the one that is mostly related to this and the reason why we are in this consortium. So I would like to start by taking some definitions and taxonomies taken from the multi-annual roadmap in robotics that you all well know. So you can, if you consider the technologies that compose a robotic system, you can classify these technologies into these 6 areas. And if you also focus on the application domains, you can also have a bunch of possible application domains divided into these 7. This is what this multi-annual roadmap in robotics is proposing. So what really does Benchmark want to do is to answer this question, whether the robots are useful or not to people in these application domains. This is not a new question. Actually, there have been and there are still ongoing several competition approaches that are trying to provide an answer to this. No? The drawback of this, there are a lot of course, advantages of having competition, but also some drawbacks, because they are mostly trying to answer if or not a robot can reach a determined goal, but not how the goal is achieved. So trying to explain a bit better this concept, if you consider, okay, that this is famous video of the failures of some of the bipedal robots during the Upper Robotics Challenge. So we have been a lot of failures, of course, also successful robots. So we like to try to provide the engineer, but also the end user, to a quantitative answer to what's really wrong, no, in that situation, why that failure happened. And we would like also to use also already existing taxonomy from multi-annual roadmap, which is the one on system abilities. I'm sure most of you already knew, because when you want to have to write a proposal on this, you have to, let's say, claim that you are going to improve a kind of one or more of the system abilities. We found this really attractive because the system abilities is a middle layer between the technology and the application domains. And this may help developers in establishing some, actually 2 main cause-effect relationships. The first one is what happens if I change the technology in my system? Actually, the behavior of my system, how is this affected by this change? And if you can establish which is the relation between an improvement of one of the systems, for example, the perception ability, how this affects one or more of the system abilities. Quantifying this would be, I think, useful for the developer. And the other one is, if I want to improve the performance of my system into an application domain, which of the system abilities is the most sensitive to this improvement? If I detect that there is one whose improvement will provide the best chances to improve the final performance, I may focus mostly on that. So in establishing these 2 cause-effect relationship, will help a lot to define a path from what I have in the lab and to what I will have in the market. So from these ideas, the Eurobench project will started. Basically, if I want to condense this into one question, is we have the system ability, but are we able to quantify each of these system ability? So the project Eurobench tried to, or is trying, because it's still an active project, to answer this question in one specific field, which is the field of bipedal locomotion, which includes prosthesis technology, power prosthesis technology, bipedal humanoids, and exoskeleton. And we would like to address the same question in NI, but focusing on a slightly different, not so different technology, which is quadrupedal locomotion, which is sufficiently close to bipedal because it's a legged locomotion system, moving in similar environment, but with, let's say, obvious differences. So the field of benchmarking is not new. It's well known, for example, computer vision, and also in many technologies that are in the market, in which you use a standard or port of reference and use this to compare your system with or assess the system. So the main focus is would like to highlight is that assessing is really important. Someone before also stressed this point. It's not only developing, but also assessing is of utmost importance. Not only to have something that can be measured in an impartial way, but also to let one system really compared with another one in all the different facets of performance, and helping the engineer to identify the critical issue and improve the system in a more efficient way. And of course, also demonstrate to the society or to the funding agency, for example, that your system is at a certain level of readiness. For example, as you can see here, this is a video from Boston Dynamics, which also developed this famous quadruped robot. And this is a video where they show how they test this system. So you can see in each of these there is a different scenario. Some of these are really simple ones. Actually, some of them are without anything, so they're measuring probably efficiency. In other, there are slightly more complex scenario, like so for example in stairs, and you will see afterwards also some more critical, like this one scenario, in which there are up and downs, also close to natural environments. So in this way, they can test and their system before introducing the market. So the main concept here is that the benchmarking is a process that is needed in order to test the system before the market introduction. So each of this company, I suppose also Anybotics, has done similar tests. The problem is that there is still not a way to do it in a rigorous and agreed way in the community. And this is what we would like to do. We have a lot of tests that have been done, a lot of demos that are shown, but they are all qualitative. We wanted in the last, say, 5 years, we started to try to propose some methods that are more, let's say, replicable, reproducible, and more quantitative. We published a paper some years ago in which we decompose all this system in the subtasks. And we introduced the concept of the environment, which is actually very important, as also said by someone before me, in which, depending on the complexity of the environment, the task will fall in a different level of complexity. This was a collaborative effort between 5 European projects. Then they merge into what is the Eurobench project. In the Eurobench project, what we have done, we have identified 3 main ingredients of benchmarking. And the first is to have test beds, as you have seen, that can replicate the real condition you can find out of the lab. Then you need protocols, you need metrics, you need algorithms to extract and to quantify the performance of and quantify these system abilities from data extracted by experiments on these test beds. And last but not least, the availability of data sets. Only by having a big data set, you can really do comparison, and you can really extract evidence or making prediction for systems. And the Eurobench is trying to do this, focusing on this bipedal system, exoskeleton, humanoids, and prostheses. And we are involved in the community. You can see here we have involved 17 different consortia in the development of all these 3 ingredients, and we are now integrating them into one big framework and 2 testing facilities, one in Madrid for wearable robots and one in Genoa for bipedal humanoids. This is a reconstruction of what will be available in 1 month here in Madrid, a place in which we can test all these things. This is a snapshot of the project that contributed to this. So we have 17 different scenarios. And yes, this is a concept that I think it would be of interest for you all. If you imagine the axis of measurability in which we can be defined like obtaining quantitative and objective information on performance, and also the axis of reproducibility, which is allowing two different teams in two different parts of the world and with two different, slightly different laboratories have results that can be comparable to each other. We have like these four areas. So the demos we have seen are falling in this area. The scientific experiments, at least in robotics, should be reproducible, but they are still not reproducible because each developers is proposing metrics that are ad hoc metrics for their experiments, but at least they are quantitative. Competition are reproducible, are done to make systems compared to each other, but most of them are really qualitative, based on yes or no. Some of these competition, like ERL, are introducing some more quantitative metrics. We would like to stay here, to have protocol and experiments which are at the same time quantitative and reproducible. Why is this important? Because from this you can really create standards and help companies really demonstrate in an agreed way that their system is working in that condition, in that scenario. So this is an example of what we have done. We have created this Lego-like irregular terrain testbed in which you can change the configuration of these modules. You can rotate these. There are 3 different inclinations, and you can have a lot of combination of different irregular terrains. And what we have done, we have created already a pre-standard. We have done, I think that we would like also to make in NI, so convert one of these testbeds into a real standard. We have done this, and it's out there. And now we're going to present this to ISO, and hopefully we will have a first international standard on irregular terrain. And we would like to start from this in the NI and try to improve this into a better, more, say, natural-like replication of the environment. So this is my last slide. I think one of the most important things is this, in this respect, in benchmarking, is to do everything together with the community. We cannot think of NI as a standalone project. We have to identify the user needs, for which are the system abilities that we would like to test, and which are the natural environment conditions that we would like to reproduce in the lab. And then the methodology, what kind of test beds, what kind of experimental protocols, and what kind of algorithm computation we need to have. And this is our group. I will be coordinating this work package, and David Rodriguez will help me in, it's a postdoc that's been hired for this project. And we are focusing on this work package, which is benchmarking and standardization. And these are also other PhD, master, and bachelor students that will stay with us during the entire project. And that's all. Thank you.